Hello and welcome to the next section. In this section, we're going to talk about the extreme value theorem again, and then we're also going to continue on to optimization. We have previously discussed the extreme value theorem, and the extreme value theorem says that if we have a function f of x and it is continuous over an interval, then it must have a maximum and a minimum value on that interval. We also looked at several graphical examples in which we had minimums and maximums. Then we officially defined an absolute maximum and an absolute minimum, and those are when we have a value, x equals c, that it is greater than every other value for maximum, or it is less than every other value for minimum. A relative maximum or minimum occur at x equals c. If those values are either greater than or less than for a minimum, then all the values in that region. We have previously only talked about this graphically, and now we're going to delve into proving it using calculus. And to prove maximum and minimums, first we have to find them. To find a maximum or minimum, we need the critical point. And to find the critical point, we just set the derivative equal to 0, and then we could solve for x. Critical points also occur when the derivative does not exist. So now we're going to do two examples. One, we're first going to talk about it in reference to the definition, and then we're going to show using calculus how to find the absolute minimum and absolute maximum. In this example, we are going to find extreme values on a closed interval. The first problem we're going to evaluate graphically. We want to find the absolute extrema on the stated interval. First, we'll start with 2 through 6. X equals 2 is right here. X equals 6 is right here. We want to find the absolute min and the absolute max. Of all of the x values on this interval, the one that is going to have the smallest output or the smallest f of x, or you could think of it as the smallest y value that will occur right here. Absolute min is at x equals 2. Then the absolute max will be right here. This is x equals 4. Next, we will look at the interval 5 through 7. This is 5 through 7. We just want to find the absolute max and the absolute min. Well, this one's not too bad. The absolute min is going to occur right here at x equals 7, and the absolute max is going to occur here at x equals 5. These produce the smallest y value and the largest y value respectively. And then finally, we want to look at the interval of x equals -3 through 5. This is a bigger interval. As we look at it, we notice first that the absolute min is here at x equals 0. There's no x value that produces a smaller y value. Now we just need to figure out where the absolute max is, and we're still going between these two green lines. I'm going to check the value that has the largest y value. Looks like that's occurring at x equals 4. Now, if there was another value I wanted to check, maybe I wanted to check right at x equals 5, I would just go here and figure out if this produced a smaller or a larger y value. In this case, it doesn't. The absolute max will be at x equals 4. Now, to find a minimum or maximum, the first thing that we need to do is find the first derivative. This will tell us where our function is increasing and decreasing, and we can narrow down potential points where those extrema occur. The domain for this function will just be -2 to 3/2. Now I want to find the derivative. The derivative of this function will be 3x squared minus 3. To find a minimum or maximum, that means that the slope at those points will be 0. If I have a max, the slope at the max would be 0. Additionally, if I have a min, the slope will be 0. We'll use this first derivative to identify potential points where this might be happening. Once I set this equal to 0, I can see that I will factor out a 3, and this will become x plus 1, x minus 1. This means I have a potential extrema at x equals -1 and x equals 1. I'm going to partition a number line just to see where we're increasing and decreasing. I need to pick a value between -infinity and -1. Let's just use -2. So -2 plus 1 times the quantity -2 minus 1. I'm using the derivative function. This will be a negative times a negative. This is positive. That means it's increasing on this interval. On the next interval, I'm going to use 0, and I get a positive times a negative. This is negative, so I'm decreasing. Then finally, I will pick a value between 1 and infinity. I'll just choose 2, and I get a positive times a positive. This is positive, so I'm increasing. What that tells me is I have a potential max here at -1 and a potential minimum here at x equals 1. But we will check these points as well as the endpoints first. To figure out if these are absolute max and absolute min, we just need to evaluate them using the function as well as evaluate the endpoints. I will find f of -1, f of 1, then I also need to find f of -2 and f of 3/2, those being the endpoints of the interval. F of -1 will just be -1 cubed minus 3 times -1 plus 2. This equals +4. Then f of 1, this will be 1 cubed minus 3 times 1 plus 2. This is 0. F of -2 will be -2 cubed minus 3 times -2 plus 2. This is 0. And finally, 3/2 cubed minus 3 times 3/2 plus 2. This equals 7/8. We are looking for the smallest and largest values on this interval. 1, 0, and -2, 0. These are the minimums. And -1, 4, this is the maximum because it is the largest output value. I always like to graph the function to double check my answers. And you'll see we do have a minimum here at -2, 0 and also at 1, 0. The other points that we checked are -1, which was an output of 4, and then we also checked 3/2. 3/2 gave us an output of 7/8 or 0.875. You can see visually this here, the -1, 4, that is the max. The -2, 0 and 1, 0, those are our mins. Let's do another example. We have the following function, natural log of x squared minus 2x plus 2, and we want to look at the interval from -1 to 2. To find the derivative, I'm going to find the derivative of the outside function, and I'm going to call this x squared minus 2x plus 2. This will be my inside function. Well, the derivative of natural log is just 1 over whatever the inside function will be. The denominator becomes x squared minus 2x plus 2. Then I want to multiply it by the derivative of the inside function. Well, that'll just be 2x minus 2. I want to set this equal to 0. This tells me where the slope of the function is 0, potentially meaning we have a maximum or a minimum. Let me just go back real fast about the domain. For the domain, the inside of the natural log function, x squared minus 2x plus 2, that has to be greater than 0. The fastest way to see this is graphically. If you plot this on a coordinate plane, you'll get a function that looks like this. There are other ways if you would like to solve it by completing the square to get the exact same information. To solve this, I just need the numerator to equal 0. Think about it. If I have 0 over 8, that's still 0. It doesn't really matter what the denominator is. 2x minus 2, this equals 0. This tells me that the slope at x equals 1 will be 0, potentially being a minimum or a maximum. I'm going to partition a number line at x equals 1. I will plug in 0 into the derivative. 2 times 0 minus 2 all over 4 minus a 4 plus 2. This will be a negative over a positive. This is negative. This will be decreasing. Then I'll pick a number on the interval from 1 to infinity. I'll just pick 2. This would be 2 times 2 minus 2. We determined that the denominator is always positive, so this is positive over positive. The whole thing's positive, and this interval will be increasing. This means that right here we have a potential minimum since we are decreasing and then we go increasing. The last step is to figure out if this is the minimum value on this interval. I will find f of 1, then I will also find the function of those endpoints, -1 and 2. F of -1 will just be natural log of 1, and that's 0. F of -1, that will just be natural log of 5, and that is approximately 1.609. And then the function of 2, this will just be the natural log of 2, which is approximately 0.693. From my calculations, it looks like f of 1 will be the min since its y value is the smallest, and then f of -1 will be the max since its y value is the largest. Then I'm just going to double check my answer by graphing. Here is that function with the bounds put on it, and we see that at x equals -1, this will be the absolute max on this interval. And at x equals 1, this will be an absolute min on this interval. And then when we checked x equals 2, this isn't a max or a min. So the steps for finding the extrema are find the derivative, set it equal to 0, then check each of those points plus the endpoints. Whichever one's the biggest, that's our max. Whichever one's the smallest, that's our min.